Hello, Oslo. They get right. Hey, you guys. Thank you very much for having me. This is amazing. This is my third year, and I just love Norway. It's just awesome. And let me tell you a few things I like, because it's been a wonderful couple of days so far. One thing I like is that I did some research, and it turns out that I'm an average Norwegian. 180 centimeters, unspecified weight, and I'm still working on getting the IQ up to the average. So if I applied for a residency in Norway, I might be just your average guy in Norway, which would be awesome. And one thing I really admire about Norwegians is they speak English like to perfection, like awesomely. Like idioms, everything. They got everything. Even they got kind of the not so nice parts of American English. For example, sometimes some Norwegian folks, I won't name names, they end a sentence like a question. You know, like, hello, I'm Jonas. I work at Cisco. And I'm like, well, I don't know your name, but Jonas sounds plausible, and I can't fix your job at Cisco. I can't help there. But I'm glad you asked. Well, it could be the opposite, which was new to me. There's folks who say a sentence, a question as a sentence. Instead of saying they go "tururup." And the other night I ate at a hotel, and then I went to have a beer. So I go have a beer, and I sit at a table, and this guy comes like a Viking, like 2 by 2, okay? 2 meters by 2 meters. And he comes and says, are you having dinner? But it's like final. It was almost as if I heard you're having dinner. And I was like, well, I didn't plan to eat again, but there's nothing I can say, so order a salad. What can you do? So I presume that guy was actually a bouncer at the restaurant, because he was like too solid and too muscular to be just server. So maybe they were shorthanded. They said, Trygve, why don't you come help here, because you're shorthanded with the waiters. And he was like, oh, sure, tips are good. I don't know why people always give me these great tips. For some reason I don't understand. So anyhow, I love Norway, and I also like one more thing. I'm going to take 30 seconds for this, because I think it's wonderful. I like if I can pronounce it properly, egalitarianism in Norway. Was it understandable? All right, I like it. Like the other night I was looking at, I was watching TV, like just flipping channels, not understanding anything, like, oh, okay, so that long. So I found like a documentary from the prisons in Norway. So they show like the interior of prison cell, which looked like, awfully good. And it was like an eerie, it was like, oh, this is deja vu all over again. I've seen this somewhere. So I'm looking at the prison cell, and it's like, this is familiar. Where did I see this? And then I look around me, so, oh, it's the same furniture in this hotel room here. Same thing, I was amazed. But anyhow, well, you guys are great, but I gotta say, you destroyed Troy Hunt this morning. Like the keynote. I thought it was hilarious. And everyone was like, yeah, well, I got that. Next one. Let's wait for the next joke. Where he had like one after another. I was chuckling a couple of times. I couldn't contain myself. And everyone was looking like, what's with this asshat here? Like, what's wrong with this guy? As if I were in the library and I was supposed to, keep my mouth shut. And so in the end, it's like, okay, so Troy has like this great talk, hilarious talk, and I was like, why isn't everybody laughing? And in the end, like, there's some golf clap. Okay, yeah, we appreciate your attempts. And then I talked to the guy, and he says, well, and I say, oh, this was brutal. And he says, oh, this is as expected. I've been in Norway before. So all right, forget all about all that. We're going to talk about efficiency today. And I have like a great task on my hands right now. I have a great task on my hands. It's a huge pressure. Here's the pride. Here's what we're going to do tonight. Last talk of the thing. I hope you're not. I'm going to be late 5 minutes. because I had to tell all this stuff, right, about Norway, right? I'm going to be late a bit. I have many slides. I have much to share with you, new content. And my hope is that by the end of this talk, all of us are going to have a sort of a mini imaginary hat, if you wish, which is our efficiency hat. Which is whenever we wear it, we're going to be able to look at things in a slightly different way. Just slightly different, which is going to allow us to find and improve those points in our programs that are less efficient than they might be. And you're gonna see tonight how we're looking at a few absolutely old classic algorithms, literally from 50 years ago. And we're going to improve them together in ways that nobody knew how to for 50 years. I'm not kidding. First, I'm going to talk about Sentinels. Who can tell us what a Sentinel is? Who's got the Viking blood in them? Come on. What's a Sentinel? Yes, please.
A special value you put somewhere so that you can track its position in some other collection. It's a special value.
It's a special value that you plant ahead of an operation to make sure that you can arrange computation in a more efficient way. Thank you. So awesome, right? So we have this Sentinel notion, and that's great because there's a joke which I hope most of you don't know yet. There's a thing with how does a programmer find an elephant in Africa? Does anyone know? Great. So this is new to you. Oh, there's one guy. Well, you can just phase out for tune off for a second here. So the joke was you put an elephant in Cairo, and you start from South Africa, and you go up north. And if you find an elephant, you're good. You look at, are you in Cairo or not? If you're in Cairo, then you didn't find any because you found yours. You see what I'm saying? Same about find, right? Let's look at the find routine. That's very simple. And I'm going to use the D language for examples here because it fits on the slides. That's how I define a generic function in the D language. You just put the type arguments first and then the regular function arguments. And I'm going to use indexed access just because it's easy. I'm going to just talk a bit about it later. So we're going to have a loop as easy as pi. So I have for I equals 0 all the way to the length of the range, which is kind of a sort of an array. You can think of a portion of an array, or a pair of iterators if you wish. I'm incrementing this good guy. And if I found the element, I'm going to break out of the loop. And now what I'm going to return is the range from that particular position all the way to $, which is a symbol for the end of the range. So if I have an array with numbers in it, I'm going to look for it, and I'm going to return the portion of the array positioned at that particular number that I found. What if I don't find the number? What do I return? Talk to me. I don't find the thing. When does the loop break? When I equals length, and here I'm going to return r from length all the way to length, which is the empty range, the sliver of the empty range just at the end of the range, which is an empty, is nothing. Right? Just like in the STR, remember you return end when you're done searching and you found nothing. You return end. In this case, you're returning the empty range. This function has been implemented millions of times in millions of languages. Everybody knows it inside and out. So today we're going to make it faster. How do we make it faster? Obviously by using Sentinels, I presume, right? So ideas? Talk to me. Yes? Sorry? Oh, yeah. So save this guy in a variable. Yes, actually it turns out that the compiler is very good at doing that already. So in good shape, thank you. But that's a good start. It's the right hat. Other ideas? Sentinels.
So it's pushing E on the back.
Huh? Right. How about I take E, I put it at the very back of the range, the last element, instead of the last element there. And then I run the search. What do I save, Hubert?
So you'll have to say what that last element was.
Yeah, so I got to save that. What computation do I save?
You don't have to worry. You know what the end is, so you don't need to do that right now either.
Awesome, thank you.
You need to find something.
Yep, this is...
You find your elephant. You're in.
Right, I find my elephant, and in the end I'm going to look at my in Cairo. Is it my elephant, which probably I painted pink, whatever, so I marked it in some way.
Somebody else's
Yeah, it's a good point. It's a good point, but Hubert, let me do the talk here. I have the microphone. All right. So I saved this work. And this is important to save, even though I add some more stuff here and here, because this is my core loop. This is where it's going to be like disproportionately much executed, right? Awesome. So let's do that. I'm going to save, as Hubert said, I'm going to save the last element of the range in a temporary C. And I'm going to push E. I'm going to just put in its place there. And then I'm going to do the loop. There's this whole scope exit thing, which means whenever this scope exit is finished here, I'm going to put the element back just to restore the previous state of affairs. And then this is my savings. This is the core loop. This is where the action is. This is where it's at, right? This is where it happens. So I have nothing here. So I'm going to save time. And here I do that whole cleanup that we're talking about. Was I just the elephant in Cairo? Is my elephant, is it pink, etc.? So this is my extra work that I'm doing, but I don't care because I do it once, right? So this is the fix-up. So that's the prelude, that's the core, this is the fix-up, and I'm done. Terrific. Now, a few details. I do this whole scope exit thing. What if something throws an exception? So I just want to preserve the range. What if the range doesn't support random access? What do I do? This doesn't apply, right? It's not going to apply anymore if the range does not support. Yes.
Fall back to the original.
Right, I got to fall back to a conservative version, which doesn't do all of these tricks. So there's a number of things I'm not going to focus on, but if you do want to focus on those, I have a talk, which you just search for ACCU 2016 and my unpronounceable and not unwritable last name, and you're going to find that talk. And it discusses these things in more depth. I eliminated that part because I want to share new material with you that's not online. It's, essentially, is never to be found. It's nowhere to be found. Okay? Great. So it doesn't work for all types, but I'm going to consider like things like integers and sort of the basic, the civilized types, right? Very nice. All right. Question: does it work or not? What do you think? How much improvement are you going to get? I don't know. Who gives like 1%? Give it 1%. Who gives 1% or more? Oh, okay. Who thinks it's going to be negative? Negative performance.
Depends on the range.
Depends on a number of things, such as the range size, because then I do a write, even if the range has like 5 elements, a write is going to be a disaster, right? Okay, let's say we kind of focus on the longer side of the, like, you know, hundreds, thousands, millions of elements, because that's where it's at, right? So does this help or not? Who gives it like positive performance? More than 0 for large, long ranges. Thank you. Yes, great. Who gives it 5%? A few hands. 10%. Anthony's like, I can't believe this is happening. All right. So actually, it turns out it's pretty good. It's pretty good. We have time in milliseconds here, and we have like millions of elements here. We're talking floating point search in a floating point array. And just to make it clear for you, I plotted the speed up in percentage compared to the baseline, which is the conservative, the simple find. And guess what? We get like awesome speed up there between like 20 and 60%. Pretty neat, you know? I could roll with that. That looks, you know, it's something I could endure to live with. Yes? Great. Excellent. You would think, however, so far I bored you because you knew all this stuff. Or worse, if you didn't know it, you didn't know it because it's not fashionable. It was, I'm not kidding, it was fashionable in the 70s. It was like, oh, those Sentinels, you know, put that in a core of ferrite, put a Sentinel there, like, you know, scribble it by hand with a knife or whatever, and that's my Sentinel right there. You can literally hold it in your hand, right? Put the Sentinel, and it was a very popular technique. And then it fell out of use. It's still very good, actually, it turns out. You just have to do the proper specialization and introspection such that you apply it only when it's applicable. For example, how about this code again? How about multiple threads execute this code? You don't. That's a bad idea. I mean, Detlef can just talk to your ear off about that, right? It's not what you want. It's not, look at it, yeah, it's not what you want. Definitely not. So there's a number of situations in which this doesn't apply, but you should apply it whenever applicable. So, you know, but this is like old things. Let's talk about new things. How about Tony Hoare's partition? Partition, the workhorse of quicksort. Who can define what partition does? Partitioning like an array. Partition. I give you an array, I give you a number, partition it for me. What does it do? Huh?
Splits it into two parts.
Splits it into parts. Well, what are the properties of those parts? Somebody else. Yes, please.
All the elements before will be less than the partition. All the elements after the partition will be greater than that partition element.
Awesome. So choose a pivot and then put the little things on the left and the greater things on the right. And that's your partition. It's used by quicksort. And quicksort is like a very important function, right? It's also used by median. Nth element, which is also very important in a bunch of algorithms, right? So, okay, so it's nice to optimize partition, right? And that's all I'm saying. So let's look at the baseline partition that is already highly optimized. I'm using a label break here, by the way, like in Java. Put a label here, put a label break here. I just want to do like 0 redundant computation. That's why I need this. Otherwise, I would need to use a go-to. And believe me, I never use go-to except when I do. I never use it except when I do, because when I do, it's awesome, right? So I do it like only for a reason, but I never do it. I never use it. Never in my life except when I do, right? So because of this labeled loop here, I can go like this. Well, here's how it works. I have low and high. So I have two variables. I got to mirror this for you. So I'm doing some awesome brain thing in real time. Like this is left, this is right. All right, you see? I'm an average Norwegian. I have the IQ, right? Okay, so I go from the left. I go from and then I find something that doesn't fit, that doesn't, it's too great. It's greater than the pivot. And I come from the right until I find something that's less than the pivot. What do I do then? It's not on the slide. It's not on the slide. Talk to me.
Rotate.
Swap them. Whoop. Put them in place. And then what do I do?
Keep going.
Go on. What do I do then? Swap again. And then what do I do? And then they meet and I'm done. This is your partition function. Think of this. It was 1956 when it was invented. At that time, it was it was like one of the first algorithms ever. It was amazing that like Tony Hoare, like genius. And let me tell you this, he also invented quicksort. It took 5 years for people to get a correct implementation of quicksort. They had bugs for 5 years in it. I'm not kidding. So it was very hard back then. It's not like, I know how to do this. Hopefully. All right, I hope I have no bugs here. So this is the loop that goes from the low portion up until I find this guy. Right, this is my pivot because I put it here, swap. I'm swapping into the first position just to put it on the left. So this is my part. I found the left bound. And then I'm continuing with going from the right with the other bound, with the high bound. And I stop if I have the pivot greater than or equal than the element, the current element. And I found the right bound. And then I'm swapping and making progress. And this is my function. At the end, I just do a little fix-up to put the pivot back where it was, and I'm done. And this is my partition function. It's a classic implementation. You would find a variant of it in the STL. Now, there's a few subtleties about it, which are interesting. Here I could use greater than, and it would still be a correct algorithm. Because, I go with low until I find something that's strictly greater than the pivot. I can just go through the equal elements. I'm fine. And there's a very subtle problem with it. What is that? Who can tell us? It's an extremely interesting problem. And similarly, I could use greater than here instead of greater than or equal, which means I go through the equal elements, I skip the equal elements, I leave them in place. What is the problem there? Genius. If all elements are the same, or you have a lot of elements that are the same, what's going to happen? Somebody else, another student here. It's an interview question. Well, what happens? Let's say everything is equal. What's going to happen then? Well, what I have here is this law is going to go all the way up. Like I start from the left and everything is the same, so everything just goes through. And I say, oh, so my partition the array in a completely useless way all the way on the right. Whereas I want partition to have some fairness in it. I want, if they're all equal, I want somewhere in the middle. Because that's a nice thing. Why is it a nice thing? Because when you quick sort, if partition goes all the way, then what do you get? Quadratic performance. Awful. So partition must be fair. Meaning whenever you have equal elements, they must kind of, they must be fairly distributed along the two halves of the array. Very interesting. It turns out there are people who had these bugs, and it was like they're like awfully difficult to diagnose, because this is going to pass all unit tests. Unit test is not going to help this. Agile is not going to help this. Scrum is not going to help this. So it's not going to be helped by those techniques. So you got to kind of really, it's difficult. Anywho, let's make it faster. Thoughts, ideas? I give you a hint. Let's use a Sentinel. How do we use a Sentinel in this case? It's a bit more complicated. So consider this. The first line there puts the pivot in the first position in the array. At the front of the array I have the pivot already. So I know that the first element is kind of less than or equal to the pivot, and also greater than or equal to the pivot, which is good information. But on the other side, I don't have a Sentinel. So I have one on the left side, but I don't have one on the right side. What do I do now? Put one on the right. Save the element. Do what you did with find. So we could do this. I did it. It doesn't save anything. It just doesn't add up. It doesn't add up. The saving is like 0.5%. It's like nothing. The function is more complicated for no good reason. So now I thought about how to minimize work here, because this is what we're looking at. We don't have an agenda to plant sentinels in places. Right? We have an agenda to optimize software. And this is what we want to do. This is what we're up for. Right? So we're looking at minimizing work here. So I want to consider this for example. Let's tell me what's overhead and what's legitimate work. For example, is this work? No, it's overhead. I'm comparing limits that have nothing to do with the algorithm. It's not work. Is this work? Yes, I'm comparing element against the pivot. I must do this. There's no way to not do this. I must look at the elements and compare them against the pivot. This is like, whatever I eliminate, this has to stay. If I don't do this, I'm not looking at all the array. I'm not doing the right thing with all elements. So this is work. This is overhead. If I'm incrementing things, I'm doing these things. These are overhead. This is work. And the comparison between low and high is overhead. So, I have a lot of overhead mixed in with the legitimate work. So we want to reduce these overheads, these comparisons and these indices, and this is also overhead, but I don't care. It's just at the end, it's not in a loop. So who gives a damn, right? Great. So let's reduce work. And here's an idea. How about we plant a sentinel in the middle, and instead of going all the way to one end, all the way to one end, we kind of put a sentinel in the middle, and we meet in the middle, and it just stops there. You can't, because you don't know where the middle is. You don't know where you're going to end up, where those guys are going to meet up. You don't know. So we can't do that. So I thought about that for an hour or so. And it's crazy, right? Well, everything I'm telling you here, and I'm saying it was easy, it's like, sleepless nights, friends. I didn't know how it's like. You do the same, right? I mean, come on, this is group therapy, right? So let's be honest. Okay, so we can't plant a sentinel in the middle. So we need to put one at each end. Now, here's the key idea. Let's put sentinels at both ends indeed. And we're going to create a vacancy. Who knows what a vacancy is? vacancy? Not at the hotel. What is a vacancy in nuclear physics? Vacancy. Anthony. It's a missing electron in a crystal. And what happens if you have a vacancy in a crystal? Attraction. So yeah, that's some, sexiness there, right? Some attraction going on. So if whatever there's a hole, another electron is going to be prone to fill that hole, that vacancy, because it's an imperfection. They're going to, by attraction, they're going to just want to migrate there. What's going to happen when that electron is going to get into the vacancy? Another vacancy. So, it's kind of essentially moving the vacancies around. And essentially, physically, what happens is that vacancy starts to behave like an electron with a positive charge. Like a positron, except it doesn't explode when it, So it's like a positron. It's a vacancy. It moves the other way. So electrons move this way, and the vacancies are moving the other way. And guess what? This is how semiconductors work. Like, there's a bunch of vacancies floating around this laptop right now. I'm not kidding. All right. So we have this vacancy idea. So here's how we apply this idea. We created an imperfection in the array. So I have an array of numbers, and we put the sentinels, and then we create a vacancy, a hole in the array. We kind of say, this is kind of an empty position in the array. And then what do? Once, let's say I have a vacancy on the far right here. What's the first thing I want to do? Fill it with what? Appropriately, right? You can't go wrong with that, right? So we come from the left and we're looking for a big element, something bigger than the pivot. Once we find it, we fill the vacancy. What happens next? What's the next phenomenon that happens? I have a new vacancy here on the left now. Oh, what do I do now? Genius! So I come from the right and I gotta fill the vacancy. Whenever I find something little, I put it in the vacancy here. And now I have a new vacancy here, and this way I'm moving the vacancies. I'm moving the vacancy for how long? What's going to happen, like, in the limit? I end up somewhere in the middle, like at the, the right partitioning point, and then what do? So they meet, the vacancy is right there at the partitioning point. Everything is greater, everything is less here. And I put a pivot back, and I'm done. So I got to save the pivot, etc. So this is all like a simple matter of programming once you got the idea. It's going to be like 3 slides. 3 slides. It's a long function. I'm not expecting you to understand every comma of it, right? It has complications. So this will be the prelude. I'm going to put the pivot in the first position, right? I have the special case here. I'm going to save the pivot, save it, because right now it's at the leftmost point of the range. So I'm going to save the pivot, I put it there, and now I plant the pivot in the end as a sentinel. So I'm going to save the old position of the last position. This is like length -1. So it's the last element in the range, the last element of the array. This is my last element. I'm going to save it, and then I'm going to bam, slap the pivot onto it. And that's my hole. That's how I start with the vacancy on that far right. And then, it's all, as I said, a matter of programming. And it turns out I get to save a bunch of work, I get to save a bunch of work, and I need to test only one for 2 of these long iterations. I save a bunch of work, which is pretty awesome. And let me kind of give you one more detail which I find is interesting here. All of this vacancy filling and stuff you can think of as a half swap. Because people usually think in terms of comparing and swapping things when they think of sorting, partitioning, etc. Actually, the whole vacancy business is half a swap. And that's great because it's more economical. What's better, to do like the temp and all that 3 steps, or just do half a swap and the other half from another point? Awesome. I'm seeing some nods here that reveal that I may get slowly to the average Norwegian IQ there, which is awesome. Thank you, Detlef. So getting there, right? So the work has become a matter of moving the vacancy around, and in the end we're going to fill it back. This is my core. It's become a lot cheaper. it's become a lot cheaper, and it does a lot more work, a lot less overhead. This is overhead, this is work, this is work, this is overhead, this is work, this is overhead, and this is work. It's like almost 50-50, and some overhead just can't escape, right? Awesome. In the end, it turns out, so I've kind of analyzed the thing, run through it, and in the end, is a bunch of fix-up you need to do. But this is how it works. It's unit tested. What can go wrong, right? So, there's a number of cases here you need to fix up at the end, because you've kind of been running real crazy with these indices here, just kind of lows, high plus 2, and etc. So there's a large fix-up part here. I don't care. It's done once. All right, so we're done with this. Let's see how good it works, how well it works. So time, milliseconds. Oh, that's pretty cool. We're looking at somewhere between like 3-5% all the way to like 25%. And guess what? This is a function that has not been improved in 50 years. It's a big deal. And moreover, this savings is going to transport into sort, because all sort does is partition. Everything else is just smoke and mirrors. Most of the workhorse is partitioning, right? So with this, it means I get to improve sort significantly. And that's awesome, and it's new, and I hope it convinces you that I got to look at these Sentinels things, right? All right. So I thought I'm smart. I thought I'm above the average Norwegian IQ. I'm not. I am not, because I did some researching of the topic. I thought I'm awesome, but actually, who's awesome? There's like 3 other people, 2 Indians and 1 Russian. So, found this paper from 2011 by Abhyagnar and Ingle, and which is it's very funny because it's one of the few papers I read which is a research paper and has the title research paper. I'm not kidding. So it's a paper entitled research paper, which I love because it's obvious what it is, right? You can't go wrong with that. So it's a research paper, entitled research paper, with the subtitle Engineering of Quicksort Partition Algorithm by these guys, and they have the same vacancy, they describe the same vacancy idea. I think it's a bit inferior because you can't choose any pivot you want. So it's just a bit more limited than our version. But this is a core idea. Also, Stepanov has recently has a nice PDF on his site. If you just Google for Stepanov partition, you're going to find a nice PDF, which discusses both Sentinels and vacancies. He calls them holes. And the nice thing is, he discusses Sentinels one chapter, discusses vacancy the next chapter, and at the end there's an exercise. Please combine both. Right? So essentially, I implemented the exercise, if you wish. But it's awesome that this is what's interesting is not that this work exists, it's that it's recent. It's not 1975, right? It's recent work. Like 2011, and Stepan wrote this like what? It was like the 2000s. Like this is recent work. And it's interesting because with the right attitude, if you wish, with the right outlook on things, you're going to find opportunity to optimize things. You may think I'm cherry picking. I'm not cherry picking. There's a bunch of work you can apply Sentinels to. Dot product of sparse vectors. Awesome application. Set intersection, same patterns. You want to merge sorted lists. The merge function, right? Merge sort. You can put a sentinel at the end. Lexicon parsing, you put a sentinel at the end. You parse your lex a lot faster. So a very great many. So we have until 40 past. Awesome. Actually, I can spend a minute here to talk about these. Dot product of sparse vectors. You have sparse vectors which are index and value, and they're sorted by index. And you go, whenever I find equal indices, I add it to the sum, right? How do I apply the sentinel here? So dot product, it's sparse vectors. Vectors, most things are 0 in a sparse vector. So you only store the non-zeros together with the index. So I have a sparse vector which has element 3.2 at position 42, and it has 0.1 at position 100, and so on, right? So this is my first sparse vector. I have another sparse vector which has the same structure. And whenever you multiply these guys, you need to find the same indices and multiply those guys together and add them up. That's the definition, scalar product, right? So how do you apply a sentinel to that layout? Yes?
Stick an entry which has
Stick something at the very end. It turns out there's subtleties. For example, I don't know. So, we've been talking about this on a forum, and essentially sort of one of the best approaches is to put like the size T max. Like the largest size T at the very end of the largest thing there, and then when you go through with it, you just have to do one test out of 3 instead of doing on each branch. So there's subtleties to it, but it can be done. Same deal about setting intersection and merging sorted lists. Lexing and parsing, how does that work? Lexing a large file, like a C++ file after pre-processing, I may add. You know, hello world, how big it is? 36,000 lines, 80 megabytes. It's amazing. It's amazing the compiler can go through with it. Like, it's a miracle of technology. It can do it in 2 seconds. Right? So you pre-process hello world. I'm not kidding. You pre-process that. Oh, actually I have it. You know what? I'm going to show you. No kidding here. All right. Is this even visible? Oh, by the way, I'm building my slides with LaTeX. And what you saw, the graphics and everything, the plots, they were generated this morning in real time. It's part of my build. So the slides are built running the benchmarks. So that you don't want to do make-j, because it's going to run 2 benchmarks at the same time. It's going to be messed up, right? Anyhow, where was I? What was I proving here? Oh, hello world. Where are you? Hello. Oh, hello.t. I don't know. Word count. 37,000 lines and 38,000 lines if you round up. And I don't know, let's see the characters. Looking at, that's like 1.2 megabytes. And that's hello world. So that's like, so this is it. This is the program. I'm telling you, the sheer fact that hello world compiles, gets into an object file, gets linked with the linker libraries and stuff, and nobody knows how a linker works, right? The sheer fact that it goes through with it, it's a miracle of technology. If I want to explain this to a guy who didn't know computing, they would say, I'm kidding there. They say, this can't be right. This is like, what's next? E to the I power of minus I pi is -1 or what? Or 1 or what? What's wrong with it, right? All right, how do you apply this to lexing and parsing this large hello world program? So here's an idea. Let's say I read a file in memory and I plop a 0 at the end, which is an invalid token, an invalid character in any C++ file, right? And then any lexing is going to have a huge big switch statement with, like, depending on the current character, you're going to do different state things, right? What do I save there? What am I saving by means of planting a 0 in a big switch statement?
Comparison.
Huh?
A comparison.
You save one comparison per character. Because otherwise you have a switch and you have at the top of the switch you have while I'm not at the end of the file. Right? So you have a big ass if inside, and inside of it a big ass switch. And inside the switch you have a nice table and everything, all the compiler knows how to optimize that. But outside that you'll have one if per character, which is crazy. So you triple the speed of things if you just put the 0 and you put the 0 as a case inside the switch, because then the cost of testing for that case is divided by the size of that big table. Right? This is awesome. So Sentinels are very much usable outside the sort of the obvious I'm going to plant an elephant there, etc. Right? So you may still think I'm cherry picking here. So let me actually switch gears here and continue with this hat on. Let me discuss a different algorithm. Who knows about selection, the selection problem? Who knows about nth element in STL? Nth element. Yes, please. I saw a hand. Oh, you just saying you heard of it? You know of it. Okay, somebody else except the thundering voice Hubert Matthews here. Nth element in the STL. Nth element, I give you an array, I give you a number, you give me, Mark?
It's a partially sorts everything that is lower than that now.
Awesome. So I give you an array, I give you half the length of the array. Nth element is going to put the smaller things on the left and the greater things on the right, thus actually giving me right at the middle what's the element that would be if the whole array were sorted. To rephrase, given an array and a number n, find what A of n would be if the array were fully sorted. You just give me one element. And you know, if on the face of it, if you approach it sort of naively, just sort the array and you're done. Just sort here, you have your answer. But actually there's a cheaper way to do it, right? There's a variant of it. Also, like Mark said, you want to place everything that's more than A of n to the left, everything that's greater to the right. There's a relationship between selection and the partition we just discussed. The partition, I choose the pivot, I partition things, but I don't know where exactly when I'm going to end up. With selection, it's exactly I want to be in this position, and I want to put everything less and everything greater. Applications. Give me the top 10 salesmen. Give me the top 100 salesmen. Find me the median height of the Norwegian male age 46, 180. That's it. I'm not kidding, right? So computing the median is very important in a bunch of applications. Great. Now, so this is also like much more important applications such as shortest path and nearest neighbor. So essentially, like a lot of computational geometry algorithms end up doing median at some point or another. So it's an important algorithm. So for those of you who don't know about QuickSelect, I'm going to introduce it to you because I think it's a very interesting and fascinating algorithm. Who knows about QuickSort? QuickSort. Most of us, right? Who knows about QuickSelect? All right, I'm very happy to introduce QuickSelect to you. Here's what QuickSelect does. It's very clever. So QuickSelect is what it does is it does the partition part like QuickSort, but you know QuickSort then recurses to the left and recurses to the right, right? Okay, QuickSelect partitions and get some pivot position, and then it looks. What am I looking for? Am I looking for an index here or here? And then lazily, kind of not lazy, cleverly, only recurses on one side, either the left or the right. So whereas QuickSort needs to fully sort the array, QuickSelect is like, I don't care for this half because my index is not there, what I'm looking for. So I'm just going to recurse on one side of the divide, of the pivot. Very interesting. So you recurse only once. What do you think the complexity of QuickSelect is? Complexity of QuickSort is all log n log n, right? So QuickSelect, which only does half as many recursions, is going to come up to, obviously for those of you who are expert mathematicians, right? Linear. But like with QuickSort, if you choose a bad pivot, systematically you're going to end up quadratic. So in a way, you know, it's even the risk is even higher here because you go all the way from linear to quadratic. In QuickSort, you go from n log n to quadratic in the worst case, right? So with QuickSelect, if you don't have a good pivot, you're completely messed up. Great. So let me show you how nice and easy QuickSelect is. I just use partition as a primitive, and all I'm doing is I recurse either here or here. I don't even care to recurse. I put a loop around it. I just reduce the range. A very simple function. Actually, I'm not kidding. This is production quality. So you don't even need to optimize it. As good as it looks, it's just production quality. You can't make it much faster. So that's great. QuickSelect. Awesome. So just to explain how it works, partition is what we discussed. It's sort of, you choose a pivot, it gives you the partitioning. And you use, QuickSelect kind of cleverly uses it repeatedly to get an exact partition where it wants to, usually during the around the median. So once you're partitioned, you're good. Great. If QuickSelect gets to eliminate any fraction of the array, then you get linear time. If you get like, sometimes if you get like all the way on the left or on the way on the right, it's not good. All right, and as we discussed, the pivot quality is the problem here. And what What techniques do you know for choosing a good pivot for quick sort? The same problem applies. Ideas for quick sort, good pivot, like find something that's about in the middle. A good pivot for quick sort, yes?
Yes, you can find the average between the left and right.
You take the median between
Yes.
probably like the left, the right, and the middle. People do that. Right. You could randomize. You could say, I'm going to randomize and kind of choose some random element. Or choose 3 random elements, compute their median, and that's my pivot. Right? So there are a number of heuristics that people use. What's the problem if you don't randomize? If you don't randomize, you choose like first, last, and middle, and you compute the median. Yes?
You get degenerate inputs.
Degenerate input, you get some patterns in the input that are completely mess you up, which are going to be quadratic, right? And actually it's plausible because it can be machine produced. So actually there's a tax you can imagine that, it's gonna. So not good. What are the problems if you do randomize? I choose a random pivot.
You want to choose a bad one anyway.
Yeah, you may end up choosing a bad one anyway. And even though, do you know this phrase in statistics? It's almost never. No, I'm not kidding actually. You know what almost never means? It's a scientific term. For those of you who don't know this science thing, almost never means the following. Let's say I throw dice, right? And again and again and again, many times. And how likely is it that I throw a 6 every time? It gets smaller and smaller and smaller, and at infinitum, it's almost never. It's possible, by the laws of physics, it's possible that it could happen, but it's going to happen almost never. And that's what almost never means in statistics. The probability of you choosing of the bad pivot by random sampling for an infinitely long array is almost never. Right? But in real life, let me tell you, so back to Earth, folks, right? Back to Earth. In real life, what happens? It's front-loaded. The first 3, if you choose 3 bad pivots in the beginning, like Anthony said, you're messed up. Choose 3 bad pivots, you're done, because that's the largest array. So if you're lucky enough to choose the first 3 pivots badly, you're going to do a lot of work that you shouldn't. And your performance is going to be like 3 times worse than otherwise, right? So even with random pivots, I'm not cool. I'm not cool at all. So that's what people do. We discussed this. So in 1961, 5 sacred monsters of algorithms: Floyd, Rivers, Tarjan, Bloom, BFE, and Pratt. So 5 sacred monsters, like very good algorithms people, they set out to prove you cannot do selection in linear time, guaranteed. There's no guarantee you can do selection in real time, in linear time. So you can on average, but you can't in the worst case. So they wanted to write a paper that would prove you can't. And they discovered an algorithm that does it. True story. So actually they're like, oh, so let's prove this can't be possibly doable. And they're like, oh, crap, man, look, it's working. I can't believe it. Right? So this is like what almost literally happened. So they found an algorithm which is called median of medians. It's a miracle of human thinking. It's amazing human ingenuity that went into that algorithm. It's one of the most elegant algorithms I've ever seen. It's godly. And it has only one little problem. We're not going to insist. It has a little problem. It's 3 to 5 times slower than anything else. That's fine, because on average, it's in the worst case, it's linear. It's just like if you want to wait 5 times more than usually, you're going to be fine. So as a consequence, it's in all books and in no implementations. Like everybody reads about it, analyzes, like, this is a good algorithm. I'm not going to use it at all from now on. I'm just going to go with the random selections and stuff. So 1961, we have 10 minutes to break that record. I am not kidding. We have 10 minutes to break that record. We're going to implement a variant of this algorithm, median of medians, that's going to beat everybody. At the Tushy. Everybody. And take names. Okay? We have 10 minutes. Are you with me these 10 minutes? It's like 3 folks in the back just leave and it's like, the hell with this. I'm not kidding. We have like what? You know, we have like a few more slides and we're done. 9 slides. Right? We can do this. So let's start with median of medians, the classic implementation. First of all, I have a particular case. If the length is less than 5, I'm just going to do it like, so it doesn't matter. If it's few elements, no, really, I do it by hand. It's just, it's a particular case. But if I have more than 5 elements, is where I compute the median of medians. And the way the median of medians goes is, you don't need to look at the indices there. The way it works is very simple. Divide the array in groups of 5 elements. So imagine like I have the first 5, next 5, next 5, and so on. Compute a median for each of those 5 elements. So now I have a fifth of the array in those little medians. That's why it's called median of medians, because I have like every 5 group has its own median. And I compute that by hand, brute force. Right? I have algorithm. I know how to do for 5 elements, I do it by hand, right? 5 elements, 1 median. 5 elements, 1 median. 5 elements, 1 median. And then I have a fifth of the array, which is the medians of medians. And then I recurse computing the median of that fifth of the array. So I get a final result, a median. Now here's the property of that number that I get. So I computed medians of each 5 groups group of 5s. And then I take that fragment of the array and I compute its median. So I get the number. It's going to be greater than half of the, by definition, it's going to be greater than half of those guys, right? But for each of those, how many other elements are smaller than it? Each of those, each of those like fifths, right, has 2 other guys that are smaller than it. Right? Are you with me? So I compute the median of that fraction of the array, and for each of those guys I have 2 others that are smaller than it. By symmetry, I also have 2 that are greater. So this median here is guaranteed to be between 3/5 and 3/10 and 7/10 of the real median. It's not going to be at the end of the array. It's going to be within a fraction of the real median. Remember when I told you a while ago that if I get to eliminate a finite fraction of the array at each step, I have linear speed? If I get to eliminate, and I get to eliminate at least 3/10 of the array by this computation. And that's how the proof goes. You compute a median of 5 by hand, you compute a median of those medians, and then you're guaranteed to be greater than 3/10, smaller than 3/10, and you eliminate those guys. One of them, at least. Right? And this is what this guy does. M5, this is going to be a brute force function. It just does it. Takes like 5 elements, 5 indices. Takes a range and 5 indices, A through E. And just, I'm not kidding. I didn't write this. I wrote on a forum and a guy did it for me. Right? I don't know his name because there's a pseudonym like TN. So there's a thread I'm giving credit in the paper, but essentially it goes like this. I wrote, guys, how do I compute median of 5 with minimum swaps and minimum comparisons? And there are like 10 folks who think that they're from Mars. They think a different way than me because I can't do this. Other people know how to. I have no idea. And actually there's a guy who who wrote a program that generated these functions. So you go, okay, so how many swaps and how many comparisons do you want? Right? I'm not kidding. So there's one with no swaps and only comparisons, and there's one with a bunch of swaps and fewer comparisons. So there's the spectrum there, right? Amazing. Anyhow, this works for 5 elements. I unit tested it, and guess what? I can unit test it for everything. Because how many permutations of 5 are there? Factorial. What's the factorial? You should compute it, my friend. You should compute it during compilation. Right? 120. So you have a 120 next permutation. It's the unit test writes itself. So this is our brute force median of 5, and we use it here as a primitive for the groups of 5. Very nice. Now here's what you do. So you take these groups of 5 and you put the medians, those medians of 5, you put in the first portion of the array. That's why I'm having the swap here. I'm going to increment j every time. And that's because I want to reuse a portion of the array instead of allocating a new array. Make sense? So I'm computing a median and then I'm putting it at the front of the array. And then the first fifth of the array is going to be the medians. And then I can continue with recursion and everything. Awesome. Now, let's make this faster together. 5 minutes. So I gave you a background, median of medians, compute medians of 5, put that in the front of the array, recurse, and you're done. And now let's make it faster. Let's make a breakthrough after 55 years. Ideas. So this is optimized up to wazoo, I guarantee. The M5 is good. So this guy we're looking at. What can we do better here? Huh? A Sentinel. No, it's not going to be a Sentinel. because, no wait, I have everything here. This is the section title here. Minimize indirect rights. So because I want to minimize indirect rights, where are most indirect rights happening? So I do the median 5, which is highly optimized, I guarantee it, and then I do the swapperoo here. And then what I'm going to do is I'm going to recurse to this fifth of the array, and I'm going to do a lot more swapperoos. So that's where the most writes are going to happen, in this the swapping here. So I'm going to essentially like make this these medians, I'm going to compute them and swap them and then swap them again, and it's just useless. It's a lot of overhead. So here's the key idea. This is a key idea. You've heard of this guy? Rob banks. A journalist asked him, why do you rob banks? Because that's where the money is. You sound unconvinced. It's like, I better rob a convenience store because they have $15.50, right? How about this? My cars are faster because they have more horsepower. Ferrari. What should you say? To get more speed, do less work. This is your hat. This is your attitude. This is your outlook. This is how you think in terms of doing less work. There are a few cases in which more work is more speed. Can someone... There's one case I know of, honest. One case, speculation. Speculative execution is more work, and you may actually throw it away, but on average it's going to be more speed. I don't know of any other case. In general, there's only so much work you can do in a finite amount of time, and you want to do less work. Otherwise, you're going to have less speed. Let's do less work. Here's idea number 1. We have 3 ideas to discuss. Idea number 1, better layout. We use this first fifth of the array, we put the medians. You don't even need to kind of understand every detail of the algorithm, but essentially there's a lot of moving data around, right, during this computation of the medians of 5. So it's kind of misses the point. We want to put, what do you want to do in partition? Put the little things on the left and put the bigger things on the right. So how about this? Remember our M5 routine, the brute force? What parameters did it take? 5, the array, the range, and 5 indices. So it actually is able to swap elements wherever they sit in the array. So how about this? Instead of choosing like the first 5 elements and the next 5 elements and the next 5, we're going to choose like this. First 2 elements, middle 2 elements, last 2 elements. We compute the median, middle element and last 2 elements. So we have 2 on the far left, 1 in the middle, 2 in the far right. That's my first group of 5. What's my next group of 5? The next 2 elements, right? The next guy in the middle there, and the next 2 on the right. And I'm doing this median of 5, which is going to statistically cleverly swap things such that the littler things are on the left, statistically. The median-ish things are in the middle, and the greater things are on the right. Yeah, it doesn't rhyme, sorry. So statistically, I'm choosing my index, I'm choosing my decomposition cleverly instead of choosing the first 5 like an idiot, the next 5 like an idiot, the next 5 like an idiot. I'm choosing like a smart guy. The average IQ Norwegian, right? I'm choosing like a smart guy. I'm choosing first 2 elements, middle element, last two elements, and then the next two elements, next middle element, and so on. So I'm going to exploit the fact that I can compute medians of any 5 indices, not only consecutive or contiguous indices. So we divide the array into 5 big subarrays. Compute a median of the first, as I said, boom, 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 right? So we're going to have, with the same swaps, we're going to statistically divide the array into littler things, median things, greater things. And this is going to be part of computing the M5. It's going to be sort of, I'm helping my next step with this step. Minimize work, right? That's where the money is. Minimize work. So after I'm done with this, amazingly, the medians of 5 are already going to be the middle quintile, the middle fifth of the array. So we're already done with 1/5 of the job. We're done. We don't need to move those guys anymore. It's done. It's a done deal. So the middle of the array is done in the first step, which was computing the median of 5, the medians of 5. And then we have the littler things here and the greater things here, and I recurse to 1/5 of the middle array, and then I'm going to do the fix-up. So amazingly, I'm going to swap a lot less element. If you do the math, is 1/10 of the array. And we're kind of done there, which is amazing. So this was the big thing that took me over so I thought about this for weeks on end. There's got to be a way to minimize those swaps. And I said, the key here is that you need to swap from non-contiguous portions of the array such that the little things go there, the big things go there. And then you're done. That's idea number 1. So it's more complicated, not by much. This is a whole function. This is a whole function, not by much. So I have idea number 1. Boom. 50% speed up. Not there yet. Not there yet. Not there yet. But you know what a scientist does? They never give up, right? So I got to rig the competition now, right? I'm kidding. So now we got to make it better. But we gained 50%, and moreover, we gained the right insight, because then every other optimization is going to compound with this one. It's not going to compete with it. And on top of this optimization, which is layout, I'm going to be able to build more. And here's what I built more. Did my research. Cenon Dumitrescu. Dumitrescu is a professor at the University of Chicago. He's a fellow Romanian, as you can tell from the last 4 letters. The fellow Romanian. And they proved a very nice conjecture. Actually, they disproved the conjecture by saying, you know what? You don't need group of 5. It's okay with groups of 3 or 4. And that's much simpler. It's cheaper to compute. So they very cleverly have an algorithm they call repeated step. And then I said, oh, so this is exactly what I need. A simpler median of 5. It's only median of 3, which is trivial. Boom. That's idea number 2. Kind of Google, right? Stack Overflow. Right? It's not a Stack Overflow, but I looked for it, and I looked for all the work in the area, and this was it. This was what I needed. It compounds with that. So I wrote the guys, I said, guys, do you do this with the, oh, no, we do all the, it's just, the algorithm was not fast, but it's fast because you compose it with this thing, with the better layout. So now you have better layout, and you have this thing. Awesome. We got to 200%. We got to 200%. We have minus 1 minute. We have 1 minute. We got to beat these guys. Got to 3x. If we get to 3x, we're done. Idea number 3, adaptation. So I ran ideas number 1 and 2, and it was great for median. It was terrible for anything but median. If you want the top 1,000 or the top 1/3, anything that's not in the middle, it was bad. So I worked on this for a long time, and then I said, well, you gotta specialize. Whenever you ask for something that's not straight in the median, you use asymmetric groups, 2 of 4 or 2 of 5. Use asymmetry to your advantage. If the index sort is small, you search a group of 2 out of 4, and you kind of get something that's biased to the left. If it's great, you get biased to the right. So, as a guy said on Twitter, you choose the happy case of all algorithms, right? So if it's in the median, I do what I just said. If it's small, I do one of these tricks, right? I choose kind of different fractions of the array. And if it's great, I choose the length minus those guys. Happy case of all algorithms. We're done. Awesome. So Google for this. Fast deterministic selection. You're going to find a very detailed draft paper on arXiv. I know how to pronounce it. arxiv.org. So you're going to find this guy, and it beats everybody to a pulp. Everybody. Like I did carefully optimized implementations of all existing algorithms. This guy beats them to a pulp. The more important graph that you may want to look at here is the speed up compared to the classic heuristics. Median of 3, randomized, ninether, and ninether randomized. Ninether is a sort of a median of 9, approximate. They call it the ninether. It's Taki's ninether. It's a famous heuristic. So these are the best ones in practice. Median of 3, randomized. I also tried median of 5. It's about as good as median of 3, so I didn't put it to not clutter anything. So what we have here is improvements between 10% here and 70% over the best in the world. Over the best in the world, friends. The best in the world. Better than the best in the world. We did it. We did it. To conclude, if you want more speed, put the hat on. You gotta do less work. Forget the Sentinels. The Sentinels are they're a mean to an end. They're not the end. The end is less work. And we saw how Sentinels are part of it, but in the second case, it was simply less swapping. Kind of just choose your layout properly such that you minimize the amount of data movement, access, the amount of writes you do, essentially. Marshal the computation to benefit you most. Arrange your computation, think of everything that influences your result and make it such that everything flows toward what you need, what you want, with minimum work. Do Aikido, if you wish, in programming. Aikido, use your opponent's power, all that stuff, right? Okay, don't do it like Vikings with the, axe there, right? Use Aikido, right? All right, and most importantly, do your research. It was very important for me to find the algorithms that the Indians and Stepanov implemented. It was very important, so I had good baselines and I could credit them properly, right? It's very important to do your research, know what people are doing in your field. Right, and in this case, if I didn't find the Chen and Dumitrescu paper, I would have been blocked because I didn't have their idea. I didn't have their insight. And without that, I would have been, that's interesting, but I'm not there. I can't get the performance. So there's treasure everywhere, as Calvin and Hobbes said, you just have to find it. So, announcement. I'm writing a book about this kind of stuff. It's called Fastware. It's a bunch of optimization techniques, such as how to benchmark, how to reduce strength, cache friendliness, indirect right elision, memoization, and the opposite of memoization, which is obliviation, hoisting and lowering, and a lot more. Thanks very much.